Today, actually, we have three different topics in today's event, and also related with FPGA. So I would like to highlight about what's our concept and also what we have done and the future plan for FPGA to accelerate the big data workload. So this is a legal notice. So this is actually, we would like to introduce ourselves. We actually a team in China and to focusing on big data area. So we usually contribute to those, open source projects like Spark or Hadoop. And also we, bridge Intel technology into those open source projects. So we would like to work a lot and work very hard for those big data area, and also to help enhance the customer experience by using Intel product. And this is actually our today's three presentation. The first one is actually to help you understand how to use FPGA to accelerate the data compression and the decompression codec by using FPGA in big data area. We actually did some of the customer demand they are asking to use FPGA to accelerate the big data area. So we have several different parts that can use FPGA in a big data workload. So the first one is actually focusing on the data compression codec by using FPGA. And the second is actually I would like to show you about two different scenarios. The first one is actually to show you about the data source parsing. It's also very hard. We will use a lot of CPU utilization when you are running the entire big data workload. And the second part is about the AI workload. We provide a new product, we call it Intel Deep Learning Accelerator. It actually is based on the FPGA, and also it is also our first product based on the FPGA, and also to provide the deep learning workload to then the FPGA can run the deep learning workload into the FPGA. So I will show you these two different use cases for today's session. And we also have another session in the last session by the end of today. It is actually to describe about how to use FPGA in YANG. So we all know YANG is actually to control the CPU resources and just use the CPU right now, but we would like to provide FPGA as the first class citizen in YANG. So we did a lot to implement this kind of feature into YANG upstream source code, and then FPGA as the first citizen resources in YANG, and then the YANG can treat the FPGA just like a CPU. So from top to down, you can see we did a lot to help convince the customer that they can use FPGA to accelerate the big data workload, and also they can control the FPGA device, just use YANG as a single a resource manager. Okay. We also got another one topic is another higher level topic. We talk about Spark circle, how to speed up the Spark circle. So this is today's presentation agenda. I will show you about the background, and also to talk about how FPGA can help the big data workload and the opportunity. Then I will show you two different cases. Okay, we did this demo for Spark Summit at San Francisco before, But since we don't have demo booths, so I just submit the presentation to show you about the result and also what we have done. So we consider about the different big data workload, and you can divide it to 3 different parts. And for those 3 different types of workload, it has their own features or characteristics about the different features. So when we consider about the FPGA design, you need to consider what kind of the problem that you would like to solve, and also to identify the problem. So we figure out these 3 different workloads, and also to identify, just like a JSON data source parsing, we use JSON format to transfer the format into Spark on self row, and then the Spark can read the data from FPGA. So we, in this kind of scenario, we figure out this kind of scenario is actually for those workloads, they all need to run this kind of scenario. So we identify it, and also to implement the IP from the FPGA, and then the FPGA can help to accelerate the big data workload. And the same scenario is just like data compression. Data compression is also very common and also very useful from those different workload types. So it may you can use FPGA to accelerate your workload. Just focusing on, we call it a pre-processing or post-processing. And also, it's more common for the big data workload, and you can just to leverage, the common part, and also to use FPGA to solve this kind of problem. Or you can just to focusing on, just like a machine learning workload, you can focusing on your target workload, like deep learning. That's why we also develop a deep learning accelerator. That is because it's really common right now, and also have a very common, well-known model you need to implement. So in deep learning accelerator, we call it a DLA. Okay, DLA we usually would like to provide some very popular network model into the DLA, and also then the user can use FPGA to run your deep learning workload into our DLA product. Okay, so it's a 2 different type of the solution, or when you are design an FPGA to run the accelerator things, that you need to consider what kind of the problem that you would like to solve. Okay, and this is a chart about our current solution. I must have to say, right now, it actually still in a very early stage to talk about if we would like to provide a total solution from FPGA to run the entire big data workload into the FPGA. But right now, what we can see is actually FPGA can solve some different problem, like although it may be a small problem, but FPGA can help a lot. Just like in network, we actually have SmartNIC to, it's also based on the FPGA, and also to use FPGA to receive the package, and also to run some other processing. If you want, you can add more IP in the FPGA. And the second part is about the data compression. I just mentioned that. So right now, the compression codec, we are based on gzip to implement the data compression IP, and also the customer can just use the gzip data compression IP to upload your workload from CPU to FPGA. And the second part, the third part is about data parsing. We did a lot about to identify the hotspot. I can show you about the result later. And also, we did this for, it's a prototype to help identify that, we can use FPGA to run the JSON parsing and also to transfer the data to the Spark. Then the Spark can read the data from FPGA directly. And the fourth part is about the data processing. It's all about what kind of the algorithm or some of the vendors they based on Intel FPGA to run circle processing in this IP to provide this kind of solution for the customer. So it depends on the customer, and also for DLA we can also focusing on this kind of solution on this stage. And the fifth part is about the encode decode. And the last one is security. So what we would like to do is actually to, I said it before, it is still in a very early stage. That is because we are still working on the small part to solve the small problem by using FPGA. But in the future, we would like to to provide an end-to-end solution, and then the end-to-end solution can just to put the entire data pipeline into the FPGA. So in the future, as you can see, FPGA card can actually to run the entire data pipeline in only a single FPGA card. This is our future plan. Okay. So we discussed with some of our customers and also define this kind of scenario. It's a very common scenario for the customer, just like we have streaming and the ETL data at the first stage, and also in this stage you may use Kafka or Spark or Hadoop in this area. And you can use our current solution about data compress or JSON parsing IP to help you offload your workload from CPU to FPGA. And then the data will be write to the data warehouse. Either it may be a BI repo directly, or it will be a machine learning model to to help the machine learning model to read the data. So our first solution is actually focusing on the data conversion and the JSON parsing. Just like I said, it is focusing on the pre-processing or post-processing data by using FPGA. This is the first one part, and the last one part is our another solution. We call it DLA. It is deep learning solution just focusing on deep learning inference. So the customer can just use a single FPGA card to run your deep learning workload from this FPGA card, and also to get a better result when we compare. When we consider during the inference, you may need to have a better low latency, or it's all about the timing. So FPGA can actually provide you a very good experience about just to target for low latency or real-time services. Okay. And what we did today is actually to put FPGA into BIGDL. So BIGDL can, just in this prototype, we as we all know, BIGDL can just provide the solution based on the CPU. So we did a ramper to then the BIGDL can help to support FPGA as well. So I will show you about the source code and also what we have done in this prototype, and also you can use this kind of prototype to help FPGA in your deep learning workload. So this is the first part, case one. So for JSON parsing, it is actually a very simple comment about transfer the data from unstructured data to a structure. So you can treat it, it is pretty easy to, but you know, the customer has a lot of this kind of request they need to processing the data a lot. Just like in our real customer case, they usually have a single cluster, and also to you know, read the data source from different source area, and also to transfer the data into the data warehouse. So this kind of scenario is actually very common, but they got a lot of you know, CPU utilization in this kind of transfer from the different data format. So what we did is to run some different micro benchmark, and also to figure out the problem. So as you can see, we run both micro benchmark for Spark streaming and also Spark Circle, and then you can see from the JSON parsing function, it really costs a lot for the CPU usage. So that's why we decided to write a prototype IP to then FPGA can use, you know, to this kind of scenario to replace the original one, and also to then the entire workload can, you know, can upload the workload from CPU to FPGA. Okay. So this is the scenario about, you know, just they need to read the data from Kafka, and also to write the data to the data warehouse. And also we read the data from the Spark. But a little bit different in our prototype, we usually transfer the data from JSON format to Spark on safe row. Then the Spark can read the data directly. It depends on what kind of the scenario you would like to use. In our scenario, we just bypass you know, the stage to write the data to the data warehouse, and then the FPGA can just process, run some pre-processing things to help, you know, passing the JSON format, and also to get the data and go to the Spark, and then the Spark can read the data directly. This is what we did. So this is the source code. We actually provide a very simple source code to just select 3 different columns from the table, and also to run 2 different tests from first one is for CPU, and the second part is for FPGA to compare about the performance. So this is the result. As you can see, it can get you know, almost 8 times performance boost from FPGA. So if you just use, you know, the magic for the FPGA is actually if there's some specific things that you would like to do for you know, by using FPGA, then it can be really provide a very good performance to you. So this is our prototype, and we think there is still some space to help enhance the performance in this in our very early stage to develop the JSON parsing IP for the customer. So it depends on what kind of the format for you. But why we choose JSON parsing later is because JSON parsing is a more complexity format when we compare to CSV or text. So it depends on your real case, and also depends on what kind of the data format you are using. and you may need to transfer it. And also the output format is also very important. And in this case, our output format is actually to read from read to Spark on several. So we transfer it to Spark. Okay. So this is the first part. And the real performance, it depends on also depends on how much input data you have. So this is our common data. Just use use 3 million rows to run the data set, and we can get 6 to 8 times performance boost from FPGA. Okay. So the second part is about the DLA. DLA actually is our first product. We call it it's based on a product we call it a pack. In Intel pack, you can provide only IP in the Intel pack, and also to run any kind of feature that you would like to implement. So we not just to provide this kind of car, we also implement the DLA IP for the customer. So the customer can just using this car, and also with the DLA IP, and to run your deep learning workload in this FPGA car. So what we did furthermore is actually to integrate into DLA, BIGDL. So for BIGDL for DLA into BIGDL. So what we did is actually based on the DLA API, we write a wrapper, and also then the customer can not just use our DLA interface. Actually, you can focus on the green part is our common API for the customer if they would like to use DLA car. It is our new toolkit. We call it Intel OpenVINO. So the customer can use OpenVINO to run their own deep learning workload. But it is a C or C++ based API. So what we would like to provide for the end customer is actually to use, for those data scientists, they may focusing on, Java or Scala or some higher level language. So what we did is actually to write a wrapper based on the DLA, and also to transfer it to BIGDL, and then the customer can just call BIGDL to use DLA car directly, and with their own familiar language, just like Java or Scala. Okay. So this is an entire scenario about what we did for DLA plus BIGDL, and we have a demo stamp about the detailed information. You just need to import the DLA library by using Java or Scala, and then you can set up some different detailed information about the DLA engine, and then you can run this kind of, you just need to call the function, and also to run a result. This is actually a prototype, so the result is really bad since we haven't have time to train in the model. Okay. So what we did, I would like to show you is actually about we did the opportunity 1. We transferred the language from C to Java-based language, and then the data scientists can directly use their familiar language to use, FPGA for their deep learning workload. And for the opportunity 2 and 3, we are still working on. The first one is the second one is actually to control both CPU and FPGA at the same level. It usually may depends on depends on the how the level you would like to control the resources. Just like in NKL, we usually have an algorithm to help handle if you have multiple CPU core, then you can use you can run multi-task or multi-thread, multi-processing in the NKL. But we all know in Spark, it's a higher level to control the the resources. So it depends on what kind of the label you would like to provide to control the resources. And what we did is actually we will put FPGA into BIGDL, then BIGDL can handle this kind of scenario. Or the customer can also use, just like I said, we have the last session to talk about how to use FPGA in YARN. So you can also use a higher level view to control the resources by using YARN to control CPU and also FPGA, become a heterogeneous platform. Okay. And the third opportunity is actually if you have multiple FPGA card, then you may also would like to, then Spark can support multiple card and also directly. So then it can have better performance. So this is what we are working on. Still not have a perfect solution, but we are working on this to discuss with the community and also to discuss with our customer about this kind of scenario. Okay. All right. So for today's presentation, I just show you several different use cases for when we consider to put the FPGA into big data workload, and also I also show you about some other opportunity and also our future plan. And we describe about the two different case study for you. So here is the call for action. You can start to try FPGA in your big data scenario. And also we provide the Intel OpenVINO toolkit for FPGA. So you can start to try this. Okay, and for any further discussion, you can contact with me directly. Thank you.
Thank you very much, Weiting. Are there any questions out there? Oh, yep.
Do you also have the benchmark for the writing? Because I saw you had a benchmark for the load stuff. I saw it there, but do you also have it for writing when you write your data, let's say, with using FPGA, or we should use it or not in terms of writing your data?
We using FPGA to read the data from the HDFS, and then to parsing the data. Since the data format in the HDFS, it is a JSON parsing format. It is JSON format. So we read the data from HDFS and also to parse the data by using FPGA, and then transfer the format to Spark unsafe row. Unsafe row is actually the data format can read by using Spark. It is an internal format in Spark. So we transfer the data by using unsafe row, and also then the Spark task can read the data directly. Okay.
Okay. Also, the prototype that you mentioned, where you have not that good result, I thought maybe you also presented this in the earlier, like some other sessions, and I was expecting to see some good results there. But you mentioned, was it a new only for this summit, or was it also presented somewhere else?
Oh, okay.
The results.
We did this demo in our demo booth at Spark Summit this year. Spark Summit at San Francisco before, but we haven't introduced by very close with the audience to talk about this. So this is why we would like to submit this kind of session to talk with our audience directly. Okay.
Yeah. Thanks for the talk. Just a question about the life cycle of an FPGA. Is the IP assigned to the FPGA once or for all or for a long time? Or is it constantly updated at each Spark task or something like this?
Okay. So it's a very interesting question that you can join with us from our latest session at the the last one. Okay. It is we actually did a feature to talk about when the Spark would like to assign an application to the Spark, and then the FPGA can dynamic to allocate their IP based on their application. So this kind of feature can help to enhance the user experience to provide a very good scenario, since the customer can just they may have so many different IP in their FPGA, and depends on their workload, they can decide what kind of the IP they would like to install into the FPGA. And then they can design this kind of solution during the workload submission. So we did this in Hadoop 3.1. So this kind of feature actually has already done. We did it in our lab, and also we submitted the entire page to the community, and right now it can be supported in Hadoop 3.1. Yep.
All right, we are out of